This question is titled, How do I win a game of NIM? Let's take a look. NIM is a very common dynamic programming problem. It comes up very often. It's a very simple game. You have two players and they're playing with piles of tokens. On each move, a player can throw away tokens from the piles, and the goal is to constrain the other player so they have no further moves. And so here, if we have a game of what they might call 1, 2, 3 NIM, you have a choice on each move. You can discard 1 token, 2 token, or 3 tokens. The first player who can't do anything loses. So if we play this game out, if there are 7 total tokens, then if I'm the player, I'll discard 3, leaving 4. If you're the challenger, you'll discard 3, leaving 1. If I'm the player, I'll discard 1, leaving 0. You can't do anything, you lose. Or I'll discard 3, leaving 4. You'll discard 1, leaving 3. I'll discard 3, leaving 0. There's nothing more that you can do, you lose. If I do this with 8 tokens, I might start by discarding 3, leaving 5. You discard 1, leaving 4. I discard 3, leaving 1. You discard 1, leaving 0, and I lose. And in fact, if we play this out, we might discover that in these latter 2 steps, there's basically nothing that I can do to win. No matter what I do, if I discard 3, leaving 1, discard 2, leaving 2, discard 1, leaving 3, you always have an option to force me to lose. And in fact, if we look at the pattern of these games, assuming both players are playing optimally, we'll see a very interesting pattern. If there are 0 tokens, I lose. It's my turn, I go first, I lose automatically. If there are 1, 2, or 3 tokens, I have a strategy, an optimal strategy I can play, which means I always win, you always lose. If there are 4 tokens, there is no optimal strategy for me to play. Any choice I make, you can have a counter choice, which causes me to lose. And we'll see a very interesting pattern here where this actually repeats, the sequence repeats. It's very much the case that any number of tokens that is evenly divisible by 4 as a starting point causes me to lose. Anything else, I win. So it's not a particularly fair game. Now, this is a particularly easy game for us to just kind of think through as a recursive formulation. We can think that if we started here, we could always decompose to here. So instead, I want to look at a slightly harder problem. Instead of 1 pile NIM, I want to look at 3 pile NIM. There's not 1 pile of tokens, there are 3 piles of tokens. And we have 3 distinct choices. In the first pile, we can remove 1 token, or we can remove 1 or 2 tokens from the second pile, or we can remove 2 or 3 tokens from the third pile. We have to do one of these 5 options, and we can't do multiple options. So we have a bunch of choices. And we can formulate this in our standard base case and inductive step recursive formulation. If there are no tokens left, I lose. If there's one token left here, I lose, because I can only remove 2 or 3 from the third pile. So there's no action I can take if there's 1 token here. I can set up my choice. I can say, if I have either of these base cases, 0, 0, 0 or 0, 0, 1, I lose. There's nothing I can do. If I have 1, 0, 0, 0, 1, 0, 0, 2, 0, whatnot, I win. Because I know for certain that there's something I can do with this step. Choose 2 from the B pile, choose 1 from the B pile, choose 1 from the C pile, or choose 2 from the C pile, choose 2. Sorry, I can't choose 2 from the C pile. Choose 2 from the C pile, choose 2 or 3 from the C pile, I win. So I can set up these 2 base cases, and they're pretty straightforward. Then, in my inductive step, I can say, it's not clear that this is a greedy problem. In fact, it's pretty clear that what choice I want to make is going to be dependent on what choices you make, which will be dependent on what choices I make, which will be dependent on what choices you make. So what I'm going to do is I'm going to maximize over the choice I make, taking into account that you are also playing optimally, that you are maximizing. So what I'm going to do is I'm going to do a little bit of like a dual max-min or a max-max, where I'm going to maximize over my choice and your choices. And so for each one of my choices, I'm going to, in this case, I'm thinking of those in terms of maximize and minimizing. I'm going to minimize over you making your choice. And so what I'm going to do is I'm going to say, for every possibility I have, for every choice you have, is there one of these choices I have at this level that result in me always winning, recursively decomposing this down to the base cases? And I can actually implement it that way. Here is my basic state of the game, piles A, B, and C. And if I'm in 0, 0, 0 or 0, 0, 1, I return a false, indicating that I lose. You can even see I'm using the brand new match statement. I can say that if I'm in any one of these states, then I know exactly what my next step would be, and it's going to force you to lose. So I return a true, and that indicates that I win. And so I have all my base cases. for my inductive step, what I can say is something like this. And I've swapped out the min and the max for an any. What I can say is, are any of my choices going to lead me to always win? So for any of my choices, is it always the case that no matter what your counter move is, I then eventually win? For every possible one of my choices, for every possible one of your counter moves. And what you can see here is this recurses. Here, the recursion is not as easy to see because it's in this call method here on this class, but I basically go through every one of my choices, then every one of your corresponding choices, and then recurse on that pairing of choices and see, is there a particular path that can be taken that allows me to win? And what this allows me to do is it allows me to identify, for a particular starting point, am I guaranteed to have a play that wins? And of course, just like in the previous problems, I can actually construct the path that I would take, the choices that I would take. But very much like my Bellman-Ford or my other problems, I may be more interested in just seeing, is there a path that exists? What's the cost of that path? How many steps does that path take? And then reconstructing this later. So here we'll just think about whether or not there is an optimal strategy, whether it is possible for you to win or not, guaranteed irrespective of how you play, if you assuming that you play optimally. And if I then want to see what those moves would be, then I can kind of construct those moves separately. And I can see that I can kind of compute these pretty easily as we go. And you can see these are all the possibilities. The problem is, boy, this is splay out. For every one of your choices, producted against every one of my choices, assuming that these are possible, assuming the move can be made. So that's at most 25 possible branches. I'm going to check the next step. So basically what I'm doing is, if this is a 5-step game, every one of those possible steps I'm splaying out by 25. This is 25 to the 5th possible steps that I have to consider. That's just too much for me to compute. And in fact, if I try to compute this, if I try and see what the answer of this is for a starting game of 5, 5, and 5, you can see how slow that is. If I try and answer this, not for 5, 5, 5, but for 6, 6, 6, just marginally greater, you can see that splay out is so aggressive that it will take me longer than I have time to actually compute this. But what I can identify from this is there is definitely optimal substructure. And I know there's optimal substructure because what we can see very clearly here is every problem can be decomposed into the optimization over a subproblem. Here, my best answer is the best answer over each one of my moves, over each one of your moves. And so every possible best play of this game is the best possible play that I can is an optimization of the best possible one-step move I can make against the worst possible, or against all the possible one-step moves you can make, recursed down until the base case. Because I have that formulation, the other thing that I can notice is I'm probably solving the same problem over and over and over, because I'm branching out here, and you can think, if I remove 2 tokens from pile C and you remove 1 token from pile A, that's kind of the same thing as if I removed 1 token from pile A and you removed 2 tokens for pile C. They get to the same point. But as a consequence of this branching, we're both computing, or both of those branches are going to recompute this. That's overlapping subproblems. And if there are overlapping subproblems, well, a simple way for me to solve that with the top-down approach is just throw a cache on top. And when I do this, I discover I can take that formulation immediately, put a cache on top, and there we get the answer for 555 and 666 very quickly. The overlapping subproblems are not generally what we're looking for at the beginning of the solution for the dynamic programming problem. Instead, what we're often looking for is that optimal substructure, the decomposition of the best possible overall choice into a maximization over a one-step choice. And to say that that has that inductive property associated with it, that we have that the optimal choice is the optimum of these choices, but we're not quite sure which choices we're going to make. And then, in order to identify which choices we can make with the minimum of recomputation, we employ something like memoization from a top-down approach or tabularization from a bottom-up approach. Now, the tabularized approach for this is a little bit tricky. And so rather than show you the tabularized approach, one of the reasons why it's a little bit tricky is it's not that simple to do. If we wanted to do the tabularized approach, we might start with some initial states. So we might have some initial states that look like this, and we might load these. So here we have some states. And this gives us, let's make that states. Let's populate. And you can see those are the initial states. What makes this a little tricky is we need to figure out how to populate the frontier of this. We can't just say something like for A in range 2 to 10, for B in range 3 or 2 to 10, and for C in range 2 to 10. Then we know that the state for A, B, and C is equal to the maximum of each of the possible choices that could be made. So this would be like the states for A minus 1. That's one choice we have. This is a pretty straightforward thinking through of how we might think about solving this, but we can't actually compute it this way. Makes it a little bit tricky. And the reason for that is, if we actually try it this way, we'll discover that the actual computation with this tabular formulation means that we have to expand on the frontier. In other words, here you can see we get a key error. The reason for that is, what we're doing is we're filling out a table, but it's a three-dimensional table where one dimension is the values of A, the other dimension is the value of B, and the third dimension is the value of C. And for each one of these elements that we fill in, we can then fill in one step further. Because we know that if we have A minus 1, B minus 1, B minus 2, C minus 2, and C minus 3 already populated, then we can populate A, B, C. If we have that populated, we can populate the next thing. So it's not as easy as writing this. We actually have to figure out what the dependencies are and encode those dependencies a little bit more directly. But I want to leave this here for you to try.